Hi everyone, welcome to, I think it's week 9 for the chemistry seminar. Do apologize that these are recorded and not live. What I will do is upload my previous chemistry seminars as well as a grade 12 exam study seminar to make up for the fact that these are recorded now. It was just that we had a lot of issues with internet connectivity and stuff over the holidays, and it was a bit of a crash. So we're going to look at acids and bases. So I want you to take 1 minute, maybe 2, write down what you know about bases. What are they? What does it mean? If you're watching the recording, you can just fast forward. But I like to do this in real time, about 35 minutes, I reckon. There's a few different definitions. So an acid donates H+, or it donates a proton because hydrogen is an electron and a proton. H+ is quite literally just a proton in a shell with a hydrogen. A base accepts. So bases are OH-. The classic example of this is if we take HCl, we add sodium hydroxide together, we get salt and water. So that's the classic acid-base reaction. Now we can look at, I'm going to break it down a bit more. So let's say we drop H+, well, let's say we drop hydrochloric acid into a solution. This is our beaker, our water level, and I'm writing in red, but kids destroyed all my whiteboard markers. So what happens is this dissociates into H+, and Cl-. Now in grade 12, you learn how to calculate the strength of acids based on their dissolution constants and stuff like that. Sorry, the dissociation constant. Can't get my words right today. So HCl dissociates into H+, which makes something acidic. Sodium, so let's take sodium hydroxide. We know because sodium is in group 1, it'll be positively charged in a compound. So we have Na+, and OH-. And it's the OH- that makes something basic. So again, take 1 minute. I want you to name as many acids and bases that you can think of. So 2 minutes. All the acids and bases, they could be just household things, they could be just about anything. I'm just going to go have a drink of water before the recording, but no. So acids and bases, what are some examples around the house? All right. Acids, things like lemon juice, lemon, lime, stomach acid, hydrochloric acid, which is used for cleaning, also used for dissolving bodies. What else have we got? Milk is an acid, slightly acidic. We have battery acid. So lemon, lime, stomach acid, hydrochloric acid, milk, battery acid. Yogurt. Yogurt is actually produced by bacteria who create lactic acid. Same stuff that makes your legs sore when you're cycling, hurts for days afterwards. It's the same stuff the bacteria use to make yogurt. So bases, soapy water. Oh, the biggest one over here is vinegar. It's gonna put this line down. I think that makes a difference. There we go, much better. Okay, bases, soapy water. We've got baking soda. We've got drain cleaner, which is sodium hydroxide. Milk of magnesia, which is like bath salts. Bleach. Okay, so now we've got some examples and we know roughly what it is. What are some of the properties of the acids and bases? So now I want the properties. What makes properties of acids, bases? So again, 2 minutes. I want you guys to take down what are the properties of the acids and bases? Like what they taste like, what they feel like. One more minute. Okay. Actually, yeah, I was thinking about. So I just drank from an adult some tropical juice. So I have a cut on my tongue and it really stings. If you've got cuts on your fingers, taste sharp. If you've got cuts on your fingers and you juice a lemon, it's going to burn like heck. They sting, they're sharp, they make you screw your face up when you eat them. Bases are slippery and they taste sour. So all of the super sour ghost drops and sour warheads we used to try and eat as kids, they're covered in a base to make them super, super painful to eat. So both of them are corrosive to metals. So battery acid is one of the strongest acids that we produce. Now I'll explain what that means shortly. If a kid or a baby swallows a little button battery, unless they get that battery out, that kid will not survive. So let's explore this term of strong. Strong acids and strong bases. So what does this mean? Not all acids and bases are created equal. Right, apologies if we look weird because I paused the recording. So we're looking at strong acids and strong bases. So we'll start with the acids. So let's say 5 hydrochloric acid molecules is enough to burn my skin. So HCl. HCl is a strong acid. That means that if I add 5H plus and 5Cl minus, or what we call complete dissociation from the parent acid, HCl, into the H plus and Cl minus. So with an acid, the more the H plus, the stronger, the greater the strength. Well, the more damage it'll do if you put it on your skin. With a weak acid, something like HF or hydrofluoric acid, we might end up with, in the solution, 2 HF molecules that didn't dissociate and only 3 H plus and 3 F minus. So this one is weak, even though we technically started with the same amount of acid. More H plus in the solution, the stronger. So it's lower H plus, so it's lower strength. Now I could sit here and go through bases, but bases are exactly the same. All right, never mind that. Just English people, apologies. So weak acid, you don't get 100% dissolution into the solution. You only get, say, 3 out of 5. Strong acid, you get H plus and Cl minus. So how do we rank the acids and bases? I want to have a think. How do we rank acids and bases on a scale? And there is a scale for this. So, give you an idea, starts with P, ends with H. Let's go. So it starts with P and ends with H. So it's from 0 to 14, with 7 in the middle. Pure water is here. Not the most flattering camera angle. So 0 to 7 are the acids. 7 to 14 are the bases. So I want you to think, let's think back to all those examples we had, and I want you to rank them from 0 to 14. We've got 2 minutes, and then we're going to go through. And then we're actually going to look at what kind of scale the pH scale is, because it's not a normal scale. All right. So acids sit at 0. Now this is a logarithmic scale. And that means that pH 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Now, this means that for every decrease in 1, it's actually 10 times the H plus levels. Over here, it's 10 times less H plus. So pH 6 is 10 times as much H plus as much H plus as pH 7. pH 5 is 100 times. pH 4 is 1,000 times. pH 3, 10,000 times. pH 2, 100,000, 1 million times. pH 0 is 10 million times. So now, again, have a think. How would that scale work backwards? We've got 30 seconds to have a think how that scale would work backwards. Or try to plot it on there. So we're talking about 0.1 times as much H plus. 0.001, 0.0001, 0.00001, 0.00001. So something at pH 0 is 10 million times more acidic than pure water. So the danger zone with the acid starts about here, 2.5. Your stomach acid inside parts of your stomach will actually burn your skin. So pH 1, pH 0, they are very dangerous chemicals that will severely burn. On the other end of the scale, you've got the bases. Which, so NaOH, sodium hydroxide or drain cleaner, in high enough concentration will melt your skin off. You can dissolve a body, most of a body using a drain cleaner. Most of the things that get stuck or clogged in your drain are organic in nature. So that's my first part about acids and bases. I'm going to upload a couple of videos on each topic. I've probably got an old one as well that I've put up, but be sure to watch. I'll probably do another one of these when we start looking at conjugate acids and bases. But if you think of the pH scale not as a linear scale, but as a logarithmic scale, each increase in number signifies a 10 times increase in potency, from the previous. I'll put out another recording probably tonight, later on tonight, with a bit more acids and bases. But I thought I'd do it in two little usable chunks.